All right, folks, let's jump into page 2. Question 8-26. Our good friend Jeremy asks, what about exterior angles? Well, in page 1, we spent all of our time talking about interior angles. Now we're going to look at exterior angles and see what we can learn about them. So part A of the problem says, in this figure, angle A is an exterior angle. So angle A is labeled right there. Are all of the exterior angles of a regular polygon equal? Well, so we're going to assume this is a regular polygon here. So we've got 6 sides, they're all equal, and 6 angles, they're all equal. And I'm going to go ahead and label this interior angle as B like we did on the front side. So we're asked, are all the exterior angles of a regular polygon equal? We know the interior angles are, but are the exterior angles equal? Well, the answer to this question is a resounding yes. And the reason is this. Because for each of these relationships here, and there are 6 of them in this figure, we have A is going to equal 180 minus B for each angle. So yes, each exterior angle of a regular polygon will have the same measure. Let's jump down to part B here. It says find A, be prepared to show how you found your answer. Well, I remember from the front side, we had this relationship that B is going to be 180 times n minus 2 over n, and for a 6-sided shape, a hexagon, we're going to have 180 times 6 minus 2 over 6, and that's 120 degrees. So that means A is going to be 180 degrees minus 120 degrees, which is 60. Part C says, what is the sum of the 6 exterior angles of a regular hexagon? Well, we have 6 of them, and they're all the same. So I'm going to use our sigma again, sum, this time of the exterior angles, abbreviating there. It's going to be 6 times 60 degrees, and that's a total of 360 degrees. So for a regular hexagon, 6 sides, the sum of the 6 exterior angles, there'd be 1 here. The sum of all 6 of those is 360 degrees. Now for part D, what we're going to do is we're going to investigate 4 other regular shapes. And we've got the equilateral triangle, the regular octagon, we know that's n equals 8. Triangles n equals 3. We got the regular decagon for n equals 10, and then the dodecagon for n equals 12. For each of these, we're going to do the same thing we just did. We're going to find the measure of the interior angle, then we're going to find the measure of the exterior angle, and then we're going to find out what the sum of all the exterior angles are. And I'm going to go ahead and do that really fast for each of these. It's pretty straightforward for the triangle. We know that if we have a equilateral triangle, each of those angles inside there is 60. We're going to do A, the exterior angle, is 180 minus 60. That's 120 degrees. So the sum of the exterior angles, we have 3 of them. Each is 120 degrees. That's 360. Okay, so that's interesting. The triangle for n equals 3 has the same, the sum of the exterior angles is the same as it was for a 6-sided shape. Let's now check out the regular octagon. So for the octagon, I found the measure of the interior angle first by doing that 180 times n minus 2, all divided by n, got 135 degrees. Then I found the exterior angle by doing 180 minus that. That gives me 45 degrees. Let's now look at the sum of the exterior angles. We have 8 of them. They're each 45 degrees. Gives me a total of 360 degrees. Well, that's interesting. That number has showed up now multiple times. We've seen it here, we've seen it here, we've seen it here. So I'm starting to see a pattern emerge. Let's jump down to the regular decagon. Okay, and again, for each of these, I'm calling B the interior angle and A the exterior angle. B is equal to 180 times n minus 2, all divided by n. That means A is 180 minus B. So one exterior angle of a regular decagon is 36 degrees. If we add all 10 of them up, 10 times 36 degrees equals our friend 360 again. Okay, so I'm starting, again, it's a little bit more evidence that we have something going on special here. Last one we're going to look at here is the regular dodecagon, 12 sides. I'm calling that interior angle B, exterior angle I'm going to squeeze in there and call it A. Each interior angle of a regular dodecagon is 150 degrees. That means each exterior angle will be 30 degrees. Sum of the exterior angles. Well, I have 12 of them, and they're each 30 degrees. That gives me that number 360 degrees again. Okay, so that's, we've seen that now multiple times. So in part E, we're asked to make a conjecture. What do you think about the sum of the exterior angles of a polygon? Well, here's what I would say. So my conjecture, a conjecture is a conclusion we make based on a pattern we observe, and I saw that pattern show up a bunch of times. I saw it up here for a hexagon, I saw it here for a triangle, saw it here for an octagon, I saw it here for a decagon, and then I saw it here for a dodecagon. So my conjecture is that the sum of the exterior angles is 360 degrees for all regular polygons. Part F asked us to do this. Is our conjecture from part E true for all polygons or only for regular polygons? Does it matter if the polygon is convex? So I'm going to jump back and look at some dynamic examples here. What I have here is a Desmos tool that shows a triangle, and each exterior angle is marked. The sum of those is shown up here, and you can see that that sum is currently 360. Watch what happens as I move the vertices around to get different size triangles, different exterior angle measures. You'll notice that that 360 doesn't change. So this is not a regular polygon anymore because all the side lengths are not the same. But that relationship still holds. I still have the sum of the exterior angles equal to 360. Let's see if it also works for quadrilaterals. Four-sided shape here, and as I move these points around to different orientations, the sum of those angles the exterior angles is staying at 360. And watch what happens here. I'm going to actually cave this bad boy in. Right now it's a convex polygon, but I'm going to cave it in right there and take a look. I still have that 360 degree relationship because this angle goes negative. Okay, so far that holds for all triangles and all quadrilaterals based on my little dynamic model that we're looking at here. What about a pentagon? Here's a five-sided shape. And again, as I move these points around, you'll notice that that exterior angle sum remains 360, even if I cave it in, even if I go concave. Okay, so that's fascinating. Why not look at it for one more? Let's look at it here for a hexagon. Yep, sure enough, that total stays 360 no matter what size or shape my hexagon is. When I say shape, I mean the angle measures. Okay, so let's jump back and finish up over here. Is our conjecture from part E true for all polygons? And I would say this. Appears to be true for all polygons, convex or concave. So what I want to do now is go back up to the conjecture I made in the previous statement, and I don't even need the word regular there anymore because that is true for all polygons. Folks, that's it. I want you to take a look at the review preview problems and let me know if you have any questions.